First of all, let me just thank Emily and Sea Grant for putting on this webinar. Hopefully it'll be of use, and I'll be happy to answer any questions either online or offline after this is over. So feel free anytime to contact me if you've got any questions that I could answer on. Let me start off by saying, what is oil? And to start with, oil it started off as CO2 in the atmosphere. And CO2 is a stable molecule. You can't burn it, and it doesn't give off any energy when you burn it. But through photosynthesis, we can add the sun's energy. And how this works is that the hydrogen atoms on water are broken off and attached to the carbon. So the first step in photosynthesis produces thousands of molecules that make up living life. Grass, it's in the summertime here, grass is growing. All of that grass is the result of photosynthesis, chemicals that are being produced by this process. But they generally have the formula, 1 carbon, 2 hydrogens, and an oxygen. So we're going from CO2 to CH2O, and we have reduced the number of oxygens in carbon dioxide, right? So that produces all of the biomass that is in our environment. Some of that biomass falls to the bottom of the oceans or is buried in the earth, and over millions and millions of years, it gets converted again. And in this, as this slide shows, we go from biomass into fossil fuels. Fossil fuels meaning oil, natural gas, coal, peat, all kinds of things like that. Specifically, we're going to be talking about the oil and oil spills. So here we go, and it shows you, this slide shows you the relative composition of carbon, oxygen, and hydrogen on these various forms. And notice as we go from carbon dioxide over to the oil, we go from carbon containing mostly oxygen to carbon containing no oxygen. In other words, the carbon is attached to hydrogen atoms, either 2 or 1, depending on the exact structure. These are called hydrocarbons, and they contain lots of energy that can be used both for metabolism and or for combustion. So this is Mother Nature's way of storing chemical energy from the sun into a material that we call fossil fuels. So what are fossil fuels actually made of? Let me slip to the next slide. These just show you some of the specific chemicals, right? They're all contain hydrogen and carbon. Some of them contain hydrogen and carbon with an approximate ratio of 1 carbon to 2 hydrogens. Others contain it with 1 carbon to 1 hydrogen. These are called aromatic compounds, right? So we start off with the types of compounds that actually make up. Oil is made up of thousands, hundreds of thousands of specific individual compounds, starting from the simplest compound, methane, all the way out to very complex molecules that may have upwards of 100 carbon atoms in them. So in this slide, we'll start off with the most common and the most concentrated individual compounds in oil, and that would be the normal alkanes. Normal alkanes are carbon and hydrogen compounds that are stretched in kind of a linear structure, right? So we start off in, at the bottom here, we call N-alkanes, where we have methyl groups on each end and a various number of methylene groups in between. These type compounds typically contain the most energy from the sun stored in the hydrocarbon compounds, right? They're the simplest. But oil, of course, is made up of very, very complex mixtures. And so we've not only got straight chain, but we've got hydrocarbons that have branches in their carbon chain. We call these isoalkanes or branched alkanes. And then it even has a mixture of cycloalkanes. In this particular diagram, I'm pointing to cyclopentane or cyclohexane, or you can have several 6-membered rings attached. And in this case, they call this a tricyclic naphthalene. But again, even though these are cyclic, they are saturate hydrocarbons. Saturate hydrocarbons contain the most energy from the sun because you've got the highest carbon-hydrogen ratio. You can also have, of these thousands and thousands of compounds, you can have cyclic structures where one ring is saturate and the other ring is an aromatic compound, right? So we have these so-called naphthenoaromatics. You can have a large variety of aromatics starting with one aromatic ring to multiple rings. Naphthalene is a two-member polycyclic aromatic hydrocarbon, up to much, much larger aromatic rings stuck together, right? So these are called the aromatic compounds. And in oil, it turns out that all of these aromatic compounds have some sort of a group attached to it. We call it the alkyl homologs. And most of the time we're talking about a methyl group, but you can have a methyl group, an ethyl group, a propyl group, an isopropyl group, butyl, and so on attached to that. So one of the things that distinguishes petroleum from other types of polycyclic aromatic hydrocarbons that are in nature is that oil has aromatic compounds, but they all have these methyl groups or other attachments to the ring structure. So now let's talk a little bit about these PAH compounds, the polycyclic aromatic hydrocarbons. One of the things we know is because of their electronic bonding structure, when these compounds are metabolized, some of them can interact and form very aggressive new compounds that attack a cell's genetic molecular structure, right? So they are known and have known to be causing cancer. The first cancer-causing compound ever detected was this compound right here that I'm outlining called benzoapyrene, right? So it is a known human carcinogen, and these are the very dangerous compounds. Good news about oil is that generally the concentration of these large carcinogenic pH compounds is fairly low, and we have a lot higher concentrations of the smaller pHs like naphthalene. Here is phenanthrene. We have acenaphthene, fluorine, and a variety of others. Now, again, in oils, you have the parent structure and you also have these alkyl homologs. But in most environmental situations, people are most concerned with the toxicity of pH compounds as opposed to the properties of other hydrocarbons that are in oil. In addition to just the straight hydrocarbons, some of the compounds in oil contain heteroatoms. For example, this compound contains a sulfur atom on this 5-membered ring, right? So you can have, this is called thiophene. This is a 5-membered ring. And in this case, we have 2 aromatic rings, so we call it dibenzothiophene. You can also have nitrogen compounds in the ring and on the outside of the ring, as well as oxygen compounds. These are called NSO compounds, and they're all part of the biomass that was converted when it was laid down in the bottom of the oceans and buried deep within the earth over millions of years, converted to oil. In addition to the straight chain saturates, the aromatics, the NSO compounds, you also have a remnant of the chlorophyll. These are called metalloporphins. And generally in oil, there are trace metals, and some of the trace metals are chelated in these metalloporphin structures. And in addition to that, you have some very large 100, up to 100 carbon atoms, molecules that are known as asphaltenes. Asphaltenes are very difficult to refine into fuels. And so these are the type compounds that are left over that the refiner doesn't find a good use for. So he sells them off to the folks that are making roof tar or roads. You mix it, you heat them up, you mix them up with sand and rock, and you pave and you make asphaltene, asphalt roads. So these are the general composition, molecular compositions of the components of oil. This slide just again restates the molecular structures. But there's some general rules which we can talk about of the chemicals that are in oil. First of all, oil is made in virtually all portions of the world, and it comes from all portions of the world. We produce a lot of oil in the Gulf Coast. It's in the South Louisiana crude, for example. Texas has West Texas crude. There's oil that's produced in Canada, Saudi Arabia, Nigeria, in all of these sections of the world, even in Siberia, for example, they have significant oil production. What we know about the chemicals in oil, that all oil contains many thousands of individual compounds. All oils, regardless of the source, contain the same type molecular structures. For example, you'll have these type molecular structures: saturated hydrocarbons, isoalkanes. Those things are in virtually all oils found anywhere in the world. But the concentration of the relative compounds change. So the molecular structures are fairly typical of oils from anywhere in the world: a North Slope Alaskan crude, the Gulf of Mexico, or the Brazilian crudes. But the quantities of the specific compounds change. So that's what makes oil different from one source to other. That the quantity of the material is there. Generally, you have the same type compounds in all of the oils. There's always an exception to that rule, but that is a general rule of thumb. And it is the quantity of these compounds that determines the physical and chemical properties. By physical properties, we're talking about things like viscosity, density. All of these properties determine where the oil goes in the environment, and the chemical properties determine how well it reacts. There are two kinds of reaction when oils are spilled in the environment. Microbes, and Joel's getting ready to discuss this process, can degrade oil, and so they have certain chemical properties where the microbes can degrade it. And Collin is going to talk about the photochemical processes. These are transformations that are producing new chemical compounds from the compounds in oil. So the oil is made up of the same structures, but the quantity of the various structures is different, and this quantity is what determines the physical properties in oil. Now, there's a whole variety of ways to look at the chemical composition of oil. Let me just say that this is, after looking at the Deepwater Horizon oil spill, I've come up with this kind of outline. We know that oil or petroleum that's coming out of the ground contains from methane all the way out to maybe up to 70 or 80 carbon atoms. But I split it into three fractions. The really volatile fraction, which includes the natural gas, C1 to C4 carbons, and the volatile compounds up to about C10. So if we look at the composition of the Macondo oil, it was mostly natural gas on a molar basis, that is the number of molecules, was mostly natural gas. In liquid oil, it's only 16%. Of course, this liquid oil is made up of bigger molecules, so it weighs more. And so on a mass basis, the gas content of the Macondo fluid was 38% natural gas, 62%. If you look at that on a pie chart down here, what we could say is, on a molar basis, the gray shows the amount of natural gas. The second fraction, C10 to C24, these are the compounds that are more or less liquid in nature and are readily degraded by normal environmental processes of normal weathering. And then you have things that don't degrade very quickly. Generally, those have 25 carbons or up. Now, this is just an approximate split, but this is how I split oil. And so what we have on the bottom, on a mass basis, is that the oil, the fluid that came out of the ground was mostly natural gas, right? It was about 27% C10 to C24 carbons, and then 19% these higher molecular weight. These are almost solid type materials. Now, when that oil was spilled, the volatile components, all the natural gas, readily dissolved into the oceans, and what came up to the surface was brought up to the surface through a riser tube. It's called the riser for it. So it's called the liquid source oil composition. And the ships at the surface bedded off most of the natural gas. So the volatile compound C1 to C10 went down significantly. And that means that the higher molecular weight compounds went up in proportion. And then you go over and you look at oil that was spilled, and again, the volatile compounds were lost from that liquid oil and the higher molecular weights. And you lose the C1 to C10 fraction quicker than you lose the C25 in up fraction. So we might ask, how do we know this? What are the analytical methods to do? And this next slide shows basically what you got to do to determine that. Scientists do it. First thing they got to do is they got to get good samples, right? So the first picture up here, people don't necessarily consider that the important step. It may be the most important step, is getting a reliable sample of what you want to analyze. That sample has collected, it has to be preserved. When it's collected, it's brought back to a laboratory, and then you go through an extraction process, whereas you take the hydrocarbons that were in the sample and put them out of the water background solvent into an organic solvent like hexane or methylene chloride, one of these extractions. When I say water, remember we're extracting water. If the oil is in the sediment, it's really attached to soils, but the soils are wet. So we've got water in a mineral material. If it's in biota, you've got the lipid materials in the biota. So we have to get the hydrocarbons out of that matrix and into a matrix that we can run through our instruments. So we collect the sample, we extract the sample, and then we go through a number of analytical techniques. Some of those analytical techniques try to separate the components, try to identify the components by separation. And those analytical devices are GC and LC. Then we have mass spectrometry, UV vis, and physical property measurements, that is density, viscosity, pore pressure, things like that. And this just limits the ways that we typically identify components of oil. Here shows the data that us crazy chemists look at, right? So we've got a gas chromatograph on top that's using a flame ionization detector. We have a gas chromatograph with a much more expensive detector called a mass spectrometer in the middle. And we can run the mass spectrometer two ways. We can run it in a general way to see everything, or we can look for specific compounds. By the way, that these big peaks that I'm showing are those normal hydrocarbons. They're straight chain hydrocarbons, and notice that they are much more concentrated. Each one of those peaks is a straight chain hydrocarbon. In the bottom, you ask the mass spectrometer to be more sensitive to detect lower levels, but it doesn't see everything that's in there. Now, there are a variety of ways that we can measure the compounds. Here is something called a gas chromatograph by gas chromatograph. We use two analytical columns before we feed it to a detector, and the detector can be a flame ionization detector or a mass spectrometer. And what we can do is this presents a composition of the oil to chemists. Now, it doesn't make any sense unless you're a chemist, but if you look at the composition of the oil, you can tell a lot about that sample. And remember, the sample of the oil changes as long as the oil is floating around in the environment and when it is absorbed by the biota or the grasses, the sea grasses, the soils and sediments. So we can follow the oil by looking at its chemical composition in these various fractions. There are a number of ways of looking at it. I showed the fractions that I choose. Oil industry uses something called Sera analysis, which they separate hydrocarbons into saturates, aromatics, resins, which are high molecular weight hydrocarbons, NSO compounds, and then the asphaltenes. And this slide from Chris Apelli in 2012 publication just shows the chromatographic differences as oil weathered in the environment and how the fractions, the saturates, the aromatics, and the oxy compounds change over time. And notice the hump gets really big and the heavy molecular weight oxy compounds get really big in this fraction. And finally, what we used in the Deepwater Horizon really for the first time was ultra high resolution mass spectrometry. These instruments cost $1 million and up. They're very expensive. They're called Fourier transform ICR mass spectrometry. So FT, ICR, MS, and you got to get the oil into the mass spectrometer. And there are a number of ways where you can ionize the oil directly without going through a gas chromatographic column. But the point is that when we take a little bit of oil and we run it through, this particular mechanism identified over 28,000 individual peaks, right? These are individual compounds that are in the oil. And we have simply never had the opportunity to understand these compounds. If we assume that these compounds are just hydrogen, carbon, nitrogen, sulfur, and oxygen, that will tell us a great deal about the composition of the oil, particularly that solid material, that asphaltenic material that doesn't go away and stays around for a long time. So these are the techniques, analytical techniques, where chemists can look at the oil and decide what's it going to do, how's it going to impact the environment, how long is it going to stay, how it's being changed, and how it's causing damage. And with that, I think I will finish